This is part 2 of the 2.2 notes on chemical bonds and compounds. So last time we talked about several things. We talked about electron configuration, that is, the electrons filling in the orbitals surrounding the nucleus of an atom. We then talked about how we can represent the outermost orbital, the valence electrons, with what we call a Lewis dot structure. And then we talked about ionic bonds. Remember, ionic bonds is where one atom is going to donate or transfer an electron from its outer valence orbital to another atom that needs an electron to fill up its valence orbital. Remember, atoms are happiest when they have full valence orbitals, so they don't like it when they have incomplete orbitals. So today we're going to continue that, talking about the second kind of bond, which is a covalent bond. Covalent bonds are different than ionic bonds. Instead of donating electrons or transferring electrons from one atom to the next, they're actually going to share electrons. Now this creates an interesting scenario called the rule of 8, or sometimes called the octet rule. With smaller atoms, what we find is that they are happiest when they have 8 electrons in their outermost orbital. This is also true about some of the larger atoms too, but it gets a little bit more complicated when you have really big atoms with lots of electrons. For the sake of biology, we really only need to worry about some of the smaller atoms, and so the rule of 8 is actually very applicable here. When we have covalent bonds, what's going to happen is instead of transferring electrons, atoms are going to hang on to their electrons and share them instead. Atoms don't really care if you're sharing an electron with another atom as long as your orbital is full. So in the example that we have here, we have an oxygen molecule. So this is 2 oxygen atoms bonded together. Oxygen has 6 valence electrons, and it wants 8 in its orbital, so what it's going to need to do is grab hold of 2 extra electrons. Now, conveniently, another oxygen atom has another 6 valence electrons, so it has 2 extra electrons that it needs to fill as well. So what these 2 oxygen atoms do is they kind of agree to share their 2 pairs of electrons, and that completes each orbital. So if you look at this diagram, you have your nucleus in the middle, and then you have 2 electrons in the first orbital, so that one's full, and now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in its second orbital. Okay, even though 2 of these 4 electrons are being shared by the other oxygen atom, it doesn't matter because this oxygen atom has its complete orbital, and that's all it cares about. This makes for stability in the atom, and this is what creates the covalent bond, is that sharing of those electrons. So when we have electrons being shared, we are creating bonds. So with covalent bonds, we can have single, double, or triple bonds depending on how many pairs of electrons we're sharing. So in this example right here, oxygen is sharing 2 pairs of electrons. So oxygen actually creates a double bond. So let's look at another example. Let's look at water, which of course we know is H2O. So water forms covalent bonds as well, so what would that look like? The easiest way to do that is to draw the Lewis dot structure of these atoms. Again, the Lewis dot structure is a very convenient diagram to help us understand how atoms are going to bond together. With water, we have H2O, so we got to start with hydrogen. So hydrogen has 1 valence electron. In fact, hydrogen is the simplest of all the atoms because it has 1 proton and typically 1 electron. But to make water, we need more than just 1 hydrogen because it's H2, so we need a second hydrogen as well. And then we need an oxygen atom. Oxygen has 6 valence electrons. It's in group 6, so there are 6 valence electrons. So we would put those electrons around the oxygen atom, going 1, 2, 3, 4, and then doubling up on 2 more electrons to give us a total of 6. Again, when you're looking at the Lewis dot structure, it becomes kind of obvious what's going to happen next. Those hydrogens are going to share their electrons with that oxygen to fill in that orbital that oxygen needs. A water molecule is going to look something like this, with each hydrogen sharing 1 electron with that oxygen. Now what this does is it completes oxygen's outermost orbital, so it has 8 electrons. Again, the octet rule, the rule of 8. But what it also does is it completes the orbital for hydrogen. Hydrogen only has that first orbital, which holds 2 electrons. So hydrogen's orbital is full, and the second hydrogen orbital is full, and then oxygen's orbital is full. So all the atoms are happy, but now they have to stick together. Now in reality, what's happening is these atoms are now creating one big electron cloud surrounding all 3 nuclei. So what holds those atoms together is that shared electron cloud. Now, a shorthand that chemists often use to represent these chemical bonds is, instead of drawing out each individual electron, is they'll just use a line to represent the pair of electrons that is being shared. So whenever you see a diagram like this, you got to remember that you have 2 electrons being shared, but we're just going to draw a single line to represent that. So each line represents a pair of electrons. So if we were to draw an oxygen molecule with 2 oxygen atoms with a double bond, you would draw 2 lines instead of 1. So to answer the earlier question, what kind of covalent bonds does water make? Well, it makes single bonds because each hydrogen is sharing 1 pair of electrons with that oxygen. So let's look at another example. Let's look at ammonia. Ammonia is NH3. So we need N, which is nitrogen. Nitrogen is in group 5, so it has 5 valence electrons. And again, you put that around the symbol N, going 1, 2, 3, 4, and then doubling up on that last electron. We also need 3 hydrogens because it's NH3. So again, what happens next is the hydrogens are going to use their electrons to fill in the empty spaces on nitrogen. And this is going to create a complete octet for nitrogen, and then again create complete pairs for hydrogen. And this creates an ammonia molecule. Again, another simple way that we can represent that is by, instead of drawing out each individual electron, we can simply draw a line to connect those elements.